Imagine you are sitting in your backyard on the night of October 4th, 1957. The sky above you is clear, the kind of clear that only exists far from city lights. Deep black, dense with stars, the Milky Way visible as a pale smear across the middle of everything. You have a shortwave radio. You have been told by a neighbor who heard it from someone else.
Flight is launched, the takeoff power will come from a rocket like this one shown in a recent test. The powerful thrust of the Aerobee sends the whole assembly up through the dense stratosphere, a layer of heavy air 50 miles thick surrounding the Earth. The first rocket is then dropped, its fuel exhausted. A second rocket ignites and takes over. Altitude 140 miles, satellite being stripped for action. It's that round ball in the nose. Altitude better than 250 miles, and the second rocket burns out, but its momentum carries the whole assembly forward.
To tune to 20 megahertz just after dark. You find the frequency. You adjust the dial. You wait, and then you hear it. Beep, 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 steady, regular. Every 0.3 of a second, without variation, without pause. A sound unlike anything that has ever come from the sky before. Not thunder, not wind, not the call of any bird or animal. A clean electronic pulse, transmitted from somewhere above the atmosphere, traveling downward through the cold October air and into your radio, and into your kitchen, and into your life. Something up there is talking, and humanity sees that any amateur radio operator on Earth could detect. Its name was Sputnik, from the Russian word for fellow traveler or traveling companion. It had been launched 4 hours earlier from a site in the Kazakh steppe called Tyuratam on a rocket that had originally been designed to carry a nuclear warhead to the United States. The rocket had failed in that purpose. It was too imprecise, too unreliable for military use. But it was powerful enough for this. It reached orbit at 9:07 p.m. Moscow time. At 9:28 p.m., it crossed over Alaska. By the time the sun rose on October 5th, Sputnik had completed one full orbit of the Earth, 40,000 kilometers in approximately 96 minutes, and was beginning its second. In Washington, D.C., the reaction was not calm. The Eisenhower administration had known Sputnik was coming. American intelligence had been tracking Soviet rocket development for years. Officials had been told, in classified briefings, that a Soviet satellite launch was likely before the end of the year. Knowing it was coming and hearing the beep were two entirely different things. Here is what that beep meant, translated from the language of physics and geopolitics into plain English. The Soviet Union had just demonstrated that it possessed a rocket powerful enough to lift a payload out of the Earth's atmosphere, accelerate it to approximately 28,000 kilometers per hour, and place it in a stable orbit. The same rocket, pointed in a different direction, loaded with a different payload, could reach any city on Earth. The beep was not just a scientific achievement, it was a message, transmitted on two frequencies, receivable by anyone with a shortwave radio, repeating every 0.3 of a second, 24 hours a day. We can reach you, Lyndon Johnson, then the Senate Majority Leader, was at his Texas ranch that evening. He had been eating dinner outdoors with friends when someone told him about the launch. He walked away from the table and stood alone for a while, looking up at the sky. He later wrote that he felt, for the first time in his life, that the sky was no longer a friendly place. It was no longer a ceiling. It had become a frontier. And the Soviets had arrived there first. The newspapers, the following morning, tried to absorb what had happened. The New York Times ran the story on the front page. The headline was measured, factual, appropriate. But the editorial pages were something different, a mixture of awe and alarm that would define the American mood for the next 12 years. How had this happened? The answer was uncomfortable. America had been complacent. The Soviet rocket program, led by a man whose name the Soviets would not reveal to the world for another decade, had been working with desperate, focused urgency toward exactly this moment. The Americans had assumed they were ahead. The beep told them they were wrong. The man responsible for Sputnik was named Sergei Korolev. He was 50 years old in 1957, and he had spent 6 years of his life in a Soviet labor camp, a gulag, during Stalin's purges, arrested on accusations that were fabricated and that everyone involved knew were fabricated. He had nearly died there. His health never fully recovered. After his release, he was put to work on the Soviet rocket program and given a title, Chief Designer, that concealed his identity entirely. The Soviets understood that he was the single most important person in their space program and that his death or capture would be catastrophic, so they hid him. His name did not appear in Soviet publications. Western intelligence agencies knew he existed but did not know who he was. He worked in an office in Moscow, then at the launch site at Tyuratam, driving his engineers with a combination of brilliance and absolute relentlessness. He slept little. He expected the same from everyone around him. He understood, with a clarity that his American counterparts had not yet achieved, that the space race was not a scientific competition. It was a demonstration of capability, of will, of what a society could accomplish when it decided that something was worth accomplishing at any cost. He had decided. The beep continued for 22 days until Sputnik's batteries died. The satellite itself orbited for 92 days before atmospheric drag slowed it enough that it began to descend. On January 4, 1958, it re-entered the atmosphere and burned up somewhere over the Bering Sea, leaving no trace. In those 92 days, it had completed 440 orbits of the Earth. During those 92 days, the United States Congress had passed emergency funding for science education. NASA had been established. The National Aeronautics and Space Administration, created by executive order in July 1958. The first American satellite had been launched. Explorer 1 on January 31, 1958, 3 months after Sputnik. It weighed 14 kilograms, compared to Sputnik's 84. America was catching up, but it was still behind. And somewhere in Moscow's, Sergei Korolev was already planning the next step. Not a satellite, not a machine, a person. If these quiet journeys through the history of human exploration help you rest tonight, consider leaving a like or subscribing. But for now, let the screens go dark. Let the beep fade. Let the October sky settle back into silence above you. Stars where they have always been, the earth turning slowly beneath them as it has always turned. Somewhere above you, right now, the International Space Station is crossing the sky at 28,000 kilometers per hour. Its crew of 7 asleep in their sleeping bags, velcroed to the walls. The Earth turning 400 kilometers below them. We never stopped going up. We just got quieter about it. Close your eyes. Part 2 is next. Yuri Gagarin was not supposed to be the one. There were 20 of them. 20 young Soviet Air Force pilots, selected from thousands of applicants, brought to Moscow in the spring of 1960 and told almost nothing about why they had been chosen or what they were being asked to do. They were given medical examinations of extraordinary thoroughness and invasiveness. They were placed in isolation chambers and centrifuges and pressure suits and dark rooms, and asked to perform tasks while their bodies were pushed to limits that no previous medical protocol had explored. They were being selected, though nobody used this word, for the most dangerous journey any human being had ever attempted. The man who would make the final selection was Sergei Korolev, the chief designer, the man whose name appeared in no Soviet publication, the man who had survived 6 years in a labor camp and come out the other side with something that functioned like absolute certainty about what mattered and what did not. He observed the 20 candidates. He read their files. He watched them in training. And he chose Yuri Gagarin. Gagarin was 27 years old. He was the son of a carpenter and a dairy farmer from a village called Klushino, roughly 180 kilometers west of Moscow. The village had been occupied by German forces during the war. Gagarin was 7 when the Germans arrived, 10 when they left. He had watched his younger brother and sister forced into labor by the occupying soldiers. He had grown up in a house damaged by the war, in a landscape damaged by the war, in a country that had lost 27 million people to the war. He was small, 157 centimeters, chosen partly because the Vosostok capsule was extremely cramped, and a larger man would not fit comfortably. He was calm in a way that the psychologist who evaluated him found difficult to quantify. He smiled easily, genuinely, the kind of smile that photographs well and that people in the same room respond to without knowing why. Korolev, who was not a sentimental man, said later that Gagarin had something, some quality of presence that the others did not. He could not define it more precisely than that. It was enough. The morning of April 12th, 1961, was cold at the Baikonur Cosmodrome in Kazakhstan. Gagarin was woken at 5:30 a.m. He ate breakfast, 2 tubes of pureed meat and 1 tube of chocolate sauce, squeezed directly into his mouth, the first meal ever eaten by someone who was about to go to space. He was helped into his pressure suit, a vivid orange that would make him easier to spot if something went wrong during landing. Then he was driven to the launch pad. The rocket waiting for him was called the R-7, a modified version of the same intercontinental ballistic missile that had launched Sputnik 4 years earlier. It stood 38 meters tall, surrounded by service towers that would retract at launch. Its engines, when ignited, would produce approximately 9 million newtons of thrust, enough to push a small apartment building into orbit. At the top of the rocket, inside a spherical capsule 3 meters in diameter, was a seat. Whether the human body, and more specifically, the human mind, could function in the complete absence of gravity. Some researchers believed that weightlessness might cause psychological disorientations so severe that a person would become unable to operate controls. Others believed the vestibular system, the inner ear mechanisms that provide the sense of balance and orientation, might generate overwhelming nausea or hallucinations. Nobody had been there. Nobody had tested it. There was no data. The Vostok capsule was therefore designed to be operated entirely automatically. Gagarin would be a passenger. The controls available to him were locked, accessible only with a 3-digit code that had been sealed in an envelope and placed in the capsule, on the theory that a man in good psychological condition would be able to open an envelope and read 3 numbers, while a man incapacitated by weightlessness would not. Before launch, one of the engineers quietly told Gagarin the code. The code was 125. At 9:07 a.m. Moscow time, the engines ignited. The sound of a rocket launching from the ground is not what most people imagine. It is not a sharp crack or an explosion. It is a sustained, physical roar felt in the chest before it is heard, that builds from a low rumble to something that overwhelms every other sensory input, a wall of sound and vibration that makes the ground shake, and the air shake and the bones shake simultaneously. Gagarin, inside his capsule at the top of the rocket, felt the vibration build beneath him. His heart rate, recorded by the medical sensors attached to his body, was 64 beats per minute. At rest, his heart rate was 64 beats per minute. He called down to the Launch Control Center. He had been asked to maintain radio contact throughout, and said a single word that has been quoted in every account of the launch written since: "Poyakali, let's go." The rocket climbed. In the first seconds, it moved slowly, enormous engines working against both gravity and the inertia of the fully fueled rocket's weight. Then faster. The service towers fell away. The launch complex shrank below. The steppe of Kazakhstan, vast and flat and brown in the early spring, spread outward in every direction. and then began to curve. Gagarin described what he saw through his porthole as the rocket climbed through the atmosphere. The sky changed color as he watched. Blue, the ordinary blue of a clear morning, deepened and darkened as the atmosphere thinned. The blue became indigo. The indigo became violet. The violet became a darkness so complete and so absolute that the stars, which are always present above the atmosphere and cannot be seen from the ground, except at night, became visible in broad daylight. He had been airborne for 9 minutes. He was in space. The capsule separated from the rocket and continued on its orbital path. Gagarin floated free of his seat, restrained by straps, but weightless, his body no longer pressing down against anything. The familiar pull of gravity simply absent. He looked out the porthole. The Earth was below him, partially obscured by cloud, its curvature visible in a way that no human eye had ever directly observed. The oceans were darker than he expected. The land masses were paler. The atmosphere, seen from above rather than from within, was a thin luminous band at the edge of the planet, impossibly thin, impossibly fragile-looking, the only thing standing between the surface and the vacuum he was currently occupying. He had a pencil in his breast pocket. In the weightlessness of orbit, he let it go and watched it float. He retrieved it. He let it go again. He ate. More food from tubes, squeezed directly into his mouth, confirming that swallowing worked in weightlessness, that the digestive system functioned without gravity to assist it. This was genuinely unknown before he did it. He reported his physical condition to ground control at regular intervals. Heart rate normal. Vision clear. Mind clear. The 3-digit code remained in its envelope, unopened. 108 minutes after launch, the retro rockets fired, and the capsule began its descent. This was the most dangerous part of the mission. The capsule had to enter the atmosphere at precisely the right angle. Too steep, and it would burn up. Too shallow, and it would skip off the atmosphere like a stone skipping off water and continue into space. The angle was correct. The heat shield held. At an altitude of 7 kilometers, the hatch blew off, and Gagarin ejected. He parachuted down separately from the capsule, a detail that the Soviets would not officially acknowledge for years, because international aviation rules at the time required a pilot to land with his aircraft to qualify for a flight record. The Soviets wanted the record, so they said he had landed with the capsule. He had not. He came down in a field near the town of Engels, in the Saratov region of Russia. A farmer and her daughter, working in the field, watched a man in an orange suit descend from the sky and land in front of them. Gagarin raised his visor and smiled. "Don't be afraid," he said. "I am a Soviet citizen." 3 weeks later, on May 5, 1961, Alan Shepard became the first American in space. His flight lasted 15 minutes and 22 seconds. It reached an altitude of 187 kilometers above the boundary of space, but not into orbit. Shepard was weightless for approximately 5 minutes. His capsule was called Freedom 7, a name chosen by Shepard himself. He splashed down in the Atlantic Ocean and was recovered by helicopter. The contrast with Gagarin's flight was not lost on anyone who was paying attention. The Soviet had orbited the Earth. The American had gone up and come back down. The Soviet mission had lasted 108 minutes. The American mission had lasted 15. In Washington, a young president who had been in office for less than 4 months sat with his advisors and asked a question that would define the next 8 years of American history. What can we do? Is there any space program which offers us hope of beating the Soviets? The answer his advisors gave him was not obvious and not safe and not guaranteed, but it was an answer. The moon. Nobody had been to the moon. Nobody had come close to the moon. Nobody had a rocket that could reach the moon. Nobody had a spacecraft that could land on the moon. Nobody had a spacesuit that could withstand the lunar surface. Nobody had a navigation system that could guide a spacecraft to the moon and back. The Soviets had Sputnik. They had Gagarin. They had momentum and capability and a head start of years. America had Alan Shepard's 15-minute flight and a question from a president who had decided that losing was not acceptable. It would be enough, but first, someone would have to die. John Kennedy had been president for 4 months when Gagarin flew. 4 months. Long enough to have authorized the Bay of Pigs invasion, a CIA-backed attempt to overthrow Fidel Castro in Cuba that failed completely and publicly, a humiliation so thorough that it damaged American credibility across the world. Long enough to have sat across a table from Nikita Khrushchev in Vienna and felt, by his own account afterward, that the Soviet premier had measured him and found him lightweight. And now, Gagarin. Kennedy was 43 years old. He was the youngest person ever elected President of the United States. He understood optics, presentation, the way a moment could be framed to mean something beyond its immediate facts. He also understood, with the cold clarity of someone who had grown up in a family that treated competition as a basic condition of existence, what it meant to be behind. He called his advisors together and asked the question directly: is there a space program which offers us hope of beating the Soviets? The advisors went away and came back with a document. It was careful, qualified, hedged in the way that government documents are always hedged. But its central conclusion was not hedged. The moon, the United States, could beat the Soviet Union to the moon. Not easily, not cheaply, not without risk of catastrophic failure, both technical and political. But it was possible if the commitment was made immediately and completely. Kennedy read the document. He sat with it for several days. Then he decided, on May 25, 1961, 20 days after Alan Shepard's 15-minute flight, Kennedy stood before a joint session of Congress and made the announcement. The speech was long. It covered many topics. The passage that history remembers was near the end. He said, "I believe this nation should commit itself to achieving the goal, before this decade is out, of landing a man on the moon and returning him safely to the earth." The applause was strong, but not unanimous. Some members of Congress understood immediately what they had just been asked to fund. Others would take time to understand. Kennedy understood. He had been briefed on the number not exist. The life support systems required did not exist. The communication systems required did not exist. The spacesuits required did not exist. The training programs required did not exist. None of it existed. Kennedy had committed to doing all of it from scratch. In less than 9 years, with technology that had not been invented yet, by engineers who had never solved any of the problems involved for a cost that nobody could accurately calculate, because nobody knew what they were building. He did it anyway. The speech that most people remember is not the one Kennedy gave to Congress. It is the one he gave on September 12, 1962, at Rice University in Houston, Texas, on a hot afternoon in front of 35,000 people, gathered in a football stadium. He had come to explain the moon program to the American public, to make them understand why it was worth the money, worth the risk, worth the years of work that lay ahead. He stood at the podium in the heat and said, "We choose to go to the moon. We choose to go to the moon in this decade and do the other things, not because they are easy, but because they are hard. Because that goal will serve to organize and measure the best of our energies and skills. Because that challenge is one that we are willing to accept, one we are unwilling to postpone, and one which we intend to win." The crowd responded the way crowds respond when someone says something that they recognize as true, even before they have thought about whether it is true. Immediately, completely, Kennedy left Houston. He had other things to deal with: Berlin, Cuba, Vietnam, 100 smaller crises that would define his presidency. The moon program would run itself now. He had set it in motion. The engineers would handle the rest. 14 months later, he was dead. The engineers he had set in motion were extraordinary. NASA, in 1961, was 4 years old. It had been created in haste in response to Sputnik by combining several existing government aeronautics research organizations and adding budget and mandate. Its workforce was talented but small, its facilities adequate but not purpose-built for what Kennedy was now asking it to do. What happened next was one of the largest organized human efforts in history. At its peak, the Apollo program employed approximately 400 seasoned people, engineers, scientists, technicians, administrators, contractors, subcontractors. It involved more than 20 zeros and companies and universities across the United States. Its annual budget at the height of the program consumed approximately 5% of the entire federal budget. To put that in perspective, NASA's current annual budget is approximately 0.5% of the federal budget. The Apollo program, at its peak, was 9 times larger relative to the federal budget than NASA's entire current operation. The money was spent on problems that had never been solved before because they had never needed to be solved before. One of those problems was fire. Specifically, how do you build a rocket and a spacecraft that will not catch fire? In space, fire is not the primary concern. There is no oxygen in space, and fire requires oxygen. But during launch and on the ground, fire is an ever-present risk. Rockets carry enormous quantities of highly flammable propellant. Spacecraft carry electrical systems, insulation, and materials that can burn. The decision NASA made in designing the Apollo capsule was to pressurize it with pure oxygen. Oxygen at higher than atmospheric concentration, making it easier for astronauts to breathe through their pressure suits during launch. Pure oxygen was lighter than a nitrogen-oxygen mixture and simpler to manage. The decision was known to carry fire risk. The risk was accepted. Schedules were tight. The Soviets were ahead. On the night of January 27, 1967, the risk became a reality. Gus Grissom had been one of the original 7 Mercury astronauts. He was 40 years old in 1967, one of the most experienced pilots in NASA, and he had been assigned to command Apollo 1, the first crewed Apollo mission, which would test the new capsule in Earth orbit before any lunar mission was attempted. Ed White was 36. He had performed the first American spacewalk in 1965, floating outside his Gemini capsule for 23 minutes above the Earth. He had described it as the most exhilarating experience of his life. Roger Chaffee was 31. He had not yet been to space. Apollo 1 was to be his first mission. On January 27th, the 3 of them were inside the Apollo capsule on the launch pad at Cape Kennedy, conducting what was called a plugs-out test, a routine ground simulation with the capsule sealed and pressurized, running through the launch sequence without actually launching. It was supposed to be the least dangerous day of the mission. The rocket was not fueled. There was no threat of explosion. This was paperwork in a spacesuit, a dry run, a checklist exercise. At 6:31 p.m., a fire started inside the capsule. The investigators, who examined the physical evidence afterward, could never determine with certainty where the fire started. The most likely origin was a bundle of wiring beneath Grissom's seat. Wiring that had been routed through an area where it could chafe against the metal structure of the capsule, wearing through the insulation over time, a spark in a pure oxygen atmosphere. Surrounded by materials, foam padding, nylon netting, Velcro, that would ignite and burn ferociously in pure oxygen. The fire spread faster than the reconstruction of events could initially credit. Within 17 seconds, the pressure inside the capsule had risen high enough to rupture the hull. The 3 astronauts could not open the hatch. The hatch design required the pressure inside the capsule to be reduced to open, and in the fire, The pressure was rising, not falling. The hatch was designed to open inward against the pressure. 17 seconds. None of them got out. The investigation that followed was brutal and thorough. It found failures at every level: engineering failures, management failures, communication failures. It found that concerns about the fire risk of pure oxygen had been raised before and not acted on. It found wiring problems that had been documented and not fixed. It found a culture inside NASA and inside the contractor, North American Aviation, that had built the capsule, in which schedule, pressure, and competitive urgency had crowded out the slower, more careful processes that safety requires. NASA stopped. Everything stopped. The Apollo program did not fly a crewed mission for 20 months. In those 20 months, the capsule was completely redesigned. The hatch was redesigned to open outward in seconds. The atmosphere was changed. A nitrogen-oxygen mixture on the ground, with pure oxygen only in space where there was nothing to burn. Hundreds of wiring issues were corrected. Materials that could burn were replaced with materials that could not. The program that emerged from the investigation was safer than the program that had existed before the fire. The 3 men who died on the launch pad, Grissom, White, and Chaffee, made the moon landing possible. This is not a comforting thing to say, and it is not meant to be. It is simply what the evidence shows. Their deaths forced a pause that produced a better machine. Kennedy never knew any of this. He had been killed in Dallas in November 1963, 4 years before the fire, 6 years before the moon landing. He did not see the program he had launched encounter its worst moment, or recover from it, or ultimately succeed. The goal he had set, a man on the moon before the end of the decade, was achieved on July 20th, 1969, with 5 months to spare. In Houston, in the weeks after the Apollo 1 fire, the engineers went back to work. They came in early and stayed late and worked weekends. Some of them had known Grissom and White and Chaffee personally. All of them knew that what had happened on the launch pad was partly the result of the speed at which they had been working. They did not work more slowly. They worked more carefully. There is a difference. The rocket they were building, the Saturn V, the largest rocket in history, was already under construction at facilities across the country. Its 5 first-stage engines, each one producing 5 million pounds of thrust, were being tested in Mississippi. Its upper stages were being assembled in California. Its guidance system was being programmed in Massachusetts. 400,000 people, all of them moving toward the same moment. The launch pad where Grissom, White, and Chaffee had died was repaired and recertified. The work continued. Imagine you are 330,000 kilometers from Earth. There is no road back. There is no rescue coming. The nearest human beings are so far away that a radio signal traveling at the speed of light takes more than a second to reach. You are 3 men in a machine, the size of a large closet, moving through the vacuum of space. at 3,200 kilometers per hour, with no margin for further error. And everything that has already gone wrong went wrong in approximately 2 seconds. Apollo 13 launched on April 11, 1970, from Kennedy Space Center. The crew was Jim Lovell, Jack Swigert, and Fred Hayes. Lovell was 42 years old and one of the most experienced astronauts in NASA. He had flown on Gemini 7, Gemini 12, and Apollo 8, the first mission to orbit the Moon, in December 1968. He had seen the lunar surface from 110 kilometers above it and come home. Apollo 13 was supposed to be his landing. Suggs Swigert had replaced the original command module pilot 3 days before launch, after the original crew member was exposed to German measles, and NASA determined he might not be immune. Swigert was good, very good, but he had never flown in space before. Apollo 13 was his first mission. Hayes was 36 and also on his first mission. He was scheduled to be the second person to walk on the lunar surface. After Lovell touched down, Hayes would follow. The landing site was a region of the Moon called Fra Mauro. The mission was planned to last 9 days. It lasted 6. The first 2 days went smoothly. The spacecraft, Odyssey, the command module, and Aquarius, the lunar module that would carry Lovell and Hayes to the surface, traveled outward from Earth on a trajectory that the navigation and computers had calculated to intersect with the Moon's position 4 days after launch. The crew ran through their checklists. They broadcast a live television tour of the spacecraft that the major networks declined to air. Space travel had become, by 1970, sufficiently routine that the networks no longer considered a crew showing viewers around their capsule to be compelling television. Nobody was watching. On the evening of April 13th, 56 hours into the mission, Swigert and Hayes performed a routine procedure, stirring the cryogenic oxygen tanks in the service module to prevent the supercooled liquid oxygen from stratifying. They flipped a switch. The switch sent electrical current to a fan inside Oxygen Tank 2. Oxygen Tank 2 had a problem that nobody knew about. During ground testing the previous year, a procedure had been used to drain the tank that involved heating the oxygen inside using electrical heaters. The heaters were supposed to operate at 28 volts. Through a series of engineering changes and documentation errors, the thermostat protecting the heaters had been changed to handle 65 volts. But the heaters themselves had not been upgraded. When 65 volts was applied during the ground test, the thermostat failed to cut off the heaters. The temperature inside the tank reached over 500 degrees Celsius, burning away the Teflon insulation on the wiring inside. Nobody knew. The tank had been closed up and installed in the service module. It had passed its subsequent tests. It looked fine from the outside. When Swigert flipped the switch to stir the fans on the night of April 13th, the damaged wiring inside Tank 2 sparked. The oxygen inside stored under pressure, supercooled, ignited. The tank ruptured. The explosion vented into the equipment bay of the service module, blowing off an outer panel and damaging oxygen tank 1 in the process. From the moment of ignition to the moment the panel blew off, approximately 2 seconds, inside Odyssey, the 3 astronauts felt a bang and a shudder. Lovell looked at the instrument panel. The readings made no sense. Multiple systems showing failures simultaneously. Pressure dropping in the oxygen system. Power dropping. Thruster activity from the spacecraft, responding to whatever had just vented from the side. Swigert called Houston. Houston, we've had a problem. The line is often misquoted as Houston, we have a problem. Swigert used the past tense. Something had already happened. Whatever it was done. Houston was not immediately certain what it was. Flight controllers worked through the telemetry, the streams of data coming down from the spacecraft, trying to reconstruct what had occurred. The data was confusing. Multiple simultaneous failures were inconsistent with any single cause they could identify quickly. It took approximately 30 minutes to understand the full situation. Oxygen tank 2 was gone. Oxygen tank 1, damaged in the explosion, was losing pressure steadily. When it was empty, the fuel cells that generated Odyssey's electricity, which operated by combining hydrogen and oxygen, would stop working. Odyssey would lose power, life support, everything. The time to total power loss was estimated at approximately 3 hours. Flight director Gene Kranz was 36 years old on the night of April 13, 1970. He had been a flight director since the Gemini program. He had a reputation for 2 things: complete calm under pressure and a white vest. He wore a different white vest for each mission, made by his wife Marta. It had become, over the years, a kind of talisman. The flight director's white vest, visible to everyone in mission control, a signal that the person wearing it was in charge and was not going to panic. Kranz gathered his controllers. The situation was this: Odyssey was dying. The crew could not land on the moon. All lunar landing resources had to be diverted to survival. The crew could not simply turn around and come home. They were past the midpoint of the journey to the moon, and the fastest route home was to continue to the moon, use its gravity to swing around the far side, and come back. They had to go to the moon to come home from the moon. The lunar module, Aquarius, was designed to support 2 people for approximately 45 hours on the lunar surface. It now had to support 3 people for approximately 90 hours in space. It had never been designed to do this. The calculations for doing it had never been done. The procedures required did not exist. Kranz told his controllers to get to work. He said words that became afterward the clearest summary of what happened in mission control over the following 4 days. He said, "I don't care about what anything was designed to do. I care about what it can do." The crew powered down Odyssey and moved into Aquarius. The lunar module was not designed to be lived in for 4 days. It was designed for 2 men. Fortitudes on the lunar surface, with the command module docked above providing additional resources. Now it had to serve as lifeboat, bedroom, kitchen, and navigation platform for 3 men with nowhere else to go. It was cold. Without the power to run heating systems, the temperature inside Aquarius dropped steadily. The crew wore their suits for warmth, but still shivered. The walls of the spacecraft were covered in condensation, equipment that had never been designed to operate in near freezing. Temperatures began behaving unpredictably. They were also increasingly being poisoned, not dramatically. Slowly, the carbon dioxide they exhaled was building up in Aquarius. The lithium hydroxide canisters designed to absorb it were being exhausted. Aquarius had enough canisters for 2 people for 2 days, not 3 people for 4 days. Odyssey had additional canisters, but the canisters for Odyssey were square. The slots in Aquarius's scrubber system were round, square canisters. Round holes in mission control. A team of engineers dumped everything available in the building onto a table. Every piece of equipment that was aboard the spacecraft exactly replicated. Plastic bags, cardboard from flight plan covers, tape, socks. Whatever was on the ship, they had to build an adapter. A way to fit a square canister into a round hole, using only materials that the crew had with them. They had to do it fast enough that the carbon dioxide levels did not reach dangerous concentrations before the adapter was ready. They did it. The procedure took hours to develop and test. It was then read to the crew over the radio, step by step, and the crew built it exactly as described. The carbon dioxide levels dropped. The burn around the moon went correctly. Aquarius fired its descent engine at precisely the calculated moment, using the moon's gravity to slingshot the spacecraft back toward Earth on a trajectory that the navigation teams in Houston had calculated under conditions that most of them would later describe as the most intense work of their lives. No computers to run the full simulation. Limited power for the navigation system. Manual calculations, checked and rechecked for a maneuver that had to be correct the first time. It was correct. The spacecraft swung around the far side of the moon, a place so remote that radio contact with Houston was impossible, the signal blocked by the lunar body itself, and emerged on the other side on a path back to Earth. For the turn to Earth, before re-entry, the crew transferred back to Odyssey, powered up on the minimal reserves that remained, enough for the final hours of the mission. Aquarius was jettisoned. It burned up in the atmosphere. Lovell, looking at it as it fell away, said goodbye to it. He said it had saved their lives. Odyssey hit the atmosphere at the correct angle. The heat shield held. The parachutes deployed. The capsule splashed down in the South Pacific at 1:07 p.m. Eastern Time on April 17, 1970. Recovery ships were already in position. All 3 crew members were recovered healthy. In mission control, Gene Kranz stood at his console and watched the splashdown data come in. Around him, the controllers, men in their 20s and 30s, who had not slept properly in 4 days, who had built procedures out of nothing and calculations out of uncertainty and a working solution out of a square canister and a round hole, stood and cheered, and some of them wept. Kranz did not weep. He stood very still and looked at the data. Then he took off his white vest. He signed it and framed it, and hung it on the wall of his office, where it remained. The mission that had failed to reach the moon had become, in the years since, the most studied and most admired mission in NASA history. Not for what it achieved in space, but for what it demonstrated on the ground. That 400,000 people working together, under impossible pressure, with inadequate resources and no margin for error, could find a way, not because the problem was easy, because they decided it was solvable. 600 million people were watching. Not together, scattered across the earth, in living rooms and public squares and bars and hospital, waiting rooms and school gymnasiums where televisions had been wheeled in on carts, in countries that were allies of the United States and in countries that were not, in cities with reliable electricity and in places where a single television set had drawn an entire village to stand outside a window and watch through the glass. 600 million people, 1/5 of the human population alive on Earth, in July of 1969, all of them watching the same thing at the same time, an event so singular that the television networks of a dozen countries had cleared their schedules entirely to carry it live, because there was nothing else worth showing. A man was about to step onto the surface of another world, and 4 days earlier, he had been standing on a launch pad in Florida, looking up at the largest machine ever built. The Saturn V rocket stood 111 meters tall. To put that in physical terms that the body can understand rather than the mind simply accepting as a number. 111 meters is taller than the Statue of Liberty, including its pedestal by a significant margin. It is taller than a 36-story building. Standing at its base and looking up at its top required tilting your head so far back that your neck ached. It weighed, fully fueled, approximately 8 million kilograms. Its 5 first-stage engines, each one larger than a house, burned through 13 metric tons of propellant per second. In the first 2.5 minutes of flight, before the first stage separated, it consumed approximately 2,000 metric tons of fuel. It was loud in a way that the word loud cannot adequately describe. The sound of a Saturn V launch was felt in the body before it was heard by the ears. A physical pressure that pushed against the chest and vibrated in the sternum, not from emotion, but from the sheer mechanical fact of sound. Waves at that intensity, moving through human tissue. Press observers stationed 3 miles from the launch pad, described feeling it at that distance. Some described it as feeling like being punched slowly and continuously from every direction simultaneously. Neil Armstrong, Buzz Aldrin, and Michael Collins rode the elevator to the top of the Saturn V at 6:45 a.m. on July 16, 1969. Armstrong was 38 years old. He was a former Navy pilot who had flown 78 combat missions in Korea before becoming a test pilot and then an astronaut. He had come closer to dying in space than almost anyone. His Gemini 8 mission in 1966 had gone into an uncontrolled spin that reached 1 revolution per second, on the edge of loss of consciousness, resolved only by Armstrong manually firing thrusters with a steadiness that the engineers reviewing the data afterward described as exceptional. He was, by most accounts, quiet, thoughtful, precise in his language in a way that reflected the precision of his thinking. He had been selected to be first on the moon not through a formal competition, but through a process that his colleagues would later describe, when pressed, as simply obvious. Armstrong was the right person. Everyone who worked with him seemed to arrive at this conclusion independently and without much deliberation. Aldrin was 39, a former Air Force pilot with a doctorate in astronautics from MIT. His thesis had been on orbital mechanics for crewed rendezvous. He was intense, meticulous, competitive in ways that he did not always successfully conceal. Collins was 38. He would not land on the moon. While Armstrong and Aldrin descended to the surface, Collins would orbit above in the command module, Columbia, alone, on the far side of the moon, out of radio contact with Earth, the most isolated human being in history, further from other people than any person had ever been. He said, in the years after the mission, that he had not felt lonely. He said he had felt aware. Launch was at 9:32 a.m. Eastern Time. The 5 F-1 engines ignited. The hold-down clamps released. The rocket lifted. Slowly at first, the same counterintuitive slowness of all Saturn V launches, the enormous mass of the vehicle requiring several seconds to overcome its own inertia before it began to move. At a rate the eye could clearly track. Then, faster, the launch tower falling away, the Florida coastline spreading below, the Atlantic Ocean appearing at the edges of the view from the cameras mounted on the rocket. Armstrong's heart rate at launch was 110 beats per minute. For comparison, Gagarin's had been 64. The journey to the moon took 4 days. The crew conducted systems checks. 8 slept in shifts. Broadcast television transmissions that were watched by millions of people, and that the crew described later as feeling slightly absurd. Floating in their spacecraft, performing demonstrations of weightlessness for an audience they could not see, narrating a journey whose destination was visible through the window as a growing circle of gray-white light. The moon grew, day by day, hour by hour, from a point of light indistinguishable from stars, to a disk, to a sphere, to a world with features craters, mountains, plains, visible to the naked eye. On July 19th, the spacecraft offered its engine to slow down enough to be captured by the moon's gravity and enter lunar orbit. They were there. From 110 kilometers above the surface, the moon looked nothing like the moon from Earth. From Earth, the moon is a flat disk, its features reduced by distance to light and shadow without depth. From orbit, it was a world, a three-dimensional landscape of extraordinary desolation, cratered and gray. Mountains casting long shadows across flat plains, the horizon curving sharply in a way that reminded you constantly that you were above a body much smaller than Earth, and completely, absolutely silent. No atmosphere, no wind, no sound of any kind had existed on that surface for billions of years. Armstrong and Aldrin moved into the lunar module Eagle. Collins stayed in Columbia. The descent began on July 20th, 1969. Eagle separated from Columbia at 1744 UKT and began the powered descent to the lunar surface. The powered descent was 12 minutes long. In those 12 minutes, more things went wrong than the mission planners had allowed for. At approximately 6,000 meters altitude, the guidance computer, a machine with 4 kilobytes of RAM, programmed by a team led by Margaret Hamilton at MIT, began displaying an alarm code. Nobody on the crew had seen a 1202 alarm in training. Armstrong called Houston. The question was implicit. Do we abort? In mission control, a 24-year-old engineer named Jack Garman had spent the previous year studying every possible alarm code the guidance computer could generate and what each one meant. He had written them on a card and kept the card at his console. He looked at his card. A 1202 alarm meant the computer was overloading, dating, receiving more data than it could process in real time, and was forced to drop lower priority tasks to keep up with higher priority ones. The critical guidance and navigation functions were in the highest priority category. They would continue regardless. The window and saw the landing site. It was wrong. The computer was guiding Eagle toward a crater, approximately the size of a football field. Its rim lined with boulders the size of cars. Landing there was not survivable. Armstrong took manual control. He flew Eagle horizontally, skimming across the lunar surface at 150 meters altitude, looking for clear ground, while the fuel gauge dropped and the clock, in mission control tracking their fuel reserve, ticked down. 60 seconds of fuel remaining. This was announced to mission control, not to Armstrong. The decision had been made not to call fuel warnings to the crew during the final approach to avoid distracting the pilot at the most critical moment. 30 seconds. Armstrong found a clear area beyond the crater. He slowed the descent. Eagle dropped at 2017 UKT on July 20th, 1969. Dust blown outward by the descent engine settled back to the surface of the moon. Eagle had landed. Armstrong's voice came over the radio, calm and precise as everything he said. Houston, Tranquility Base here. The Eagle has landed. In mission control, the flight controller managing the descent, Charlie Duke, tried to respond and found that his voice had stopped working properly. He tried again. Roger, tranquility. We copy you on the ground. You've got a bunch of guys about to turn blue. We're breathing again. Thanks a lot. Armstrong and Aldrin were supposed to sleep before the moonwalk. They did not sleep. Nobody expected them to sleep. The idea that two human beings who had just landed on the moon would lie down for 6 hours of rest before going outside was, in retrospect, optimistic to the point of absurdity. NASA had included the sleep period in the timeline for legitimate physiological reasons. Armstrong and Aldrin requested to skip it. Houston agreed. At 02:56, Unit T. Vilsel on July 21, 1969, Neil Armstrong descended the ladder of Eagle's descent. Stage paused at the bottom rung and stepped onto the surface of the moon. He said, "That's one small step for man, one giant leap for mankind." He had intended to say, "one small step for a man." The article making the contrast between an individual human and all of humanity more precise. The radio transmission dropped the article. He said, "Man and mankind." 2 words meaning the same thing, the contrast lost. He has spent the decades since explaining what he meant to say. It does not matter. 600 million people heard the words. 600 million people understood what was happening. The exact phrasing was beside the point. A human being was standing on another world. Armstrong walked on the moon for 2 hours and 31 minutes. He collected rock samples. He took photographs. He planted an American flag with a horizontal wire along the top to keep it extended, since there was no wind on the moon to unfurl it. He spoke by telephone to President Nixon, who called from the White House in what Nixon described as the most historic phone call ever made from the White House. Aldrin joined him 20 minutes after Armstrong stepped off the ladder. He looked around at the lunar surface, the gray regolith, the black sky, the Earth hanging above the horizon, and used one word to describe it: magnificent desolation. 2 words, not one. But the compression was right. It was magnificent. It was desolate. It was both things simultaneously, in a way that no single word could hold. They left the surface of the moon at 1754 UNCR on July 21st. The ascent stage of Eagle fired its single engine and rose from the lunar surface, leaving behind the descent stage the flag, the seismometer they had deployed, and a plaque attached to the descent stage leg that read, "We came in peace for all mankind." Eagle rejoined Columbia in lunar orbit. Collins, who had been orbiting alone while his crewmates walked on the moon, brought them aboard. The crew began the journey home. On July 24th, Columbia splashed down in the Pacific Ocean. Recovery ships were in position. The 3 astronauts were pulled from the capsule and placed in biological isolation. NASA was taking no chances with potential lunar contaminants, however unlikely their existence, and flown to a quarantine facility in Houston. They had been gone 8 days, 3 hours, 18 minutes, and 35 seconds. They had gone to the moon and come back. It had worked. In the hours after the splashdown, in cities across the earth, people who had stayed awake through the night or gathered around televisions, in the middle of their day, went back to their ordinary lives. The groceries still needed buying. The children still needed feeding. The work that had been set aside for the moon landing still needed doing. The world looked the same as it had 8 days earlier, except that it wasn't. Something had shifted. Not in the physical arrangement of things, but in what was understood to be possible. For most of human history, the moon had been a light in the sky, something to navigate by, to write poems about, to attribute tides and madness and romance to. On July 20th, 1969, it became a place where people had been. The shift was permanent. The moon, from that night forward, was somewhere humanity had stood. And the question, where else, was already being asked. After Apollo 11, the world moved on, not immediately, not all at once, but faster than NASA had expected, and faster than the astronauts who followed Armstrong and Aldrin to the lunar surface had prepared themselves for. The moon had been reached. The goal Kennedy had set in 1961 had been achieved. The Soviet Union had not landed anyone on the moon. America had won the race, clearly and completely, in front of 600 million witnesses. And so the question that the American public began to ask, with a speed that surprised everyone inside NASA, was, why are we still going? It was not an unreasonable question. It was, however, the wrong one. Apollo 12 launched on November 14th, 1969. 4 months after Apollo 11. The crew was Pete Conrad, Alan Bean, and Richard Gordon. Conrad was 39, a Navy test pilot, with a gift for irreverence that made him one of the most liked people in the astronaut corps. When he stepped onto the lunar surface, he was aware that the world was listening for something as memorable as Armstrong's first words. He stepped off the ladder and said, "Whoopee, man, that may have been a small one for Neil, but that's a long one for me." Conrad was 5 feet 6 inches tall. Armstrong was 5 feet 11. The remark was exactly what it appeared to be, a short man making a joke about a tall man's step. It was also, in its relaxed, unscripted humanity, something that Armstrong's carefully considered words had not quite been. The world barely noticed. The television networks covered Apollo 12 with a fraction of the attention they had given Apollo 11. One broadcast was cut short to return to regular programming. Viewers did not complain in significant numbers. The moon, 4 months after the first landing, had become ordinary. Apollo 12 had a specific scientific mission that Apollo 11 had not. The target landing site was chosen not for safety, as Armstrong's Tranquility Base had been, but for precision. NASA wanted to demonstrate that it could land a spacecraft at a specific pre-selected point on the lunar surface. rather than simply finding a flat area in a general region. The target was the Surveyor 3 probe, an unmanned American spacecraft that had landed on the Moon in April 1967 and had been sitting on the lunar surface in the ocean of storms. For 2.5 years, Conrad landed Eagle within 163 meters of Surveyor 3. For context, he had navigated 380 thousand kilometers through space and landed within the length of 1.5 football fields of a specific object. Bean and Conrad walked to Surveyor 3 and removed parts of it, the camera, tubing, structural pieces, to be brought back to Earth for analysis. Scientists wanted to know what 2.5 years of exposure to the lunar environment had done to the materials. One of the findings was unexpected. A bacterium, Streptococcus mitis, was found surviving inside the surveyor's camera. It had been there since the probe launched from Earth. It had survived 2.5 years of vacuum, radiation, and temperature extremes on the lunar surface. This finding was subsequently disputed. Most scientists believe the contamination occurred during the analysis on Earth rather than during lunar exposure, but for a period it raised the extraordinary possibility that life could survive on the Moon. It probably cannot, but for a moment it seemed like it might. Apollo 13, which we have already followed through its near catastrophe, was followed by Apollo 14. Alan Shepard commanded Apollo 14. He was 47 years old, the oldest person to walk on the Moon, and he had waited 9 years for this mission. He had been the first American in space in 1961, a 15-minute suborbital flight that felt, in retrospect, like a beginning. Then an inner ear condition had grounded him for years, removed from flight status, while his colleagues flew Gemini and Apollo missions without him. Surgery corrected the condition in 1969. He lobbied for a mission. He got Apollo 14 on the lunar surface. Shepard produced a makeshift golf club, a 6-iron head attached to a sample collection handle, and hit 2 golf balls. The first shot went into a crater. The second, he said, went miles and miles and miles in the 1/6 gravity of the Moon, with no atmosphere to slow the ball. A well-struck golf shot would travel approximately 2 kilometers. Shepard's shot, according to subsequent analysis of the footage, traveled approximately 24 meters. He was wearing a pressure suit with limited shoulder mobility. The miles and miles remained in the folklore of the space program, one of its most cheerful exaggerations. Apollo 15, 16, and 17 carried something that the earlier missions had not: a car. The lunar roving vehicle was a 4-wheeled electric vehicle designed to extend the range of moonwalks beyond what an astronaut could cover on foot. It weighed 210 kilograms on Earth, 35 kilograms in lunar gravity, and could carry 2 astronauts plus equipment at a maximum speed of approximately 18 kilometers per hour across the lunar surface. It folded up to fit inside a storage compartment on the lunar module's descent stage and unfolded after landing. Dave Scott and James Irwin drove it on Apollo 15 in July and August of 1971. They covered 9 kilometers across the surface near Hadley Rill, a sinuous channel carved into the lunar surface, possibly by ancient volcanic activity. They found a rock that became known as the Genesis Rock, a piece of the moon's original crust formed approximately 4.1 billion years ago, carried to the lunar surface by geological processes over billions of years, and picked up by a human hand. On Apollo 16, John Young and Charlie Duke drove 26.7 kilometers across the Descartes Highlands. Young was 41, a veteran of Gemini and Apollo 10, and he had a habit of jumping, repeatedly catching himself in the air. Delighted by what 1/6 gravity did to a man who knew how to jump. The footage of Young jumping on the moon is one of the most purely joyful things ever recorded. 8. Apollo 17 was the last. It launched on December 7, 1972, the only nighttime launch of the Apollo program. And the Saturn rising from Kennedy Space Center lit the sky for hundreds of miles in every direction, visible from as far away as North Carolina. The crew was Gene Cernan, Harrison Schmitt, and Ron Evans. Schmitt was a geologist, the only trained scientist to walk on the moon, added to a late Apollo crew after pressure from the scientific community, who had grown frustrated that all the men collecting geological samples were pilots rather than geologists. He found an orange soil near a crater that turned out to be volcanic glass beads, evidence of ancient fire fountaining on the lunar surface. Billions of years old, Cernan was the commander. On December 14, 1972, he was the last person to climb the ladder back into the lunar module before departure. He had written his daughter Tracy's initials in the lunar soil, TDC, for Teresa Dawn Cernan, knowing that with no wind and no weather, they might remain there for millions of years. Before he climbed the ladder, he said, "We leave as we came, and God willing, as we shall return, with peace and hope for all mankind." He climbed the ladder, the ascent engine fired. Apollo 17 left the lunar surface at 5:54 p.m. Eastern Time on December 14, 1972. No human being has stood on the moon since. That fact is worth sitting with for a moment. The Apollo program demonstrated, across 6 successful landings over 3.5 years, that human beings could travel to another world, work there, and return safely. It demonstrated this 12 times. 12 people walked on the moon, with a reliability that, given the complexity of what was being done, was extraordinary. And then it stopped. Not because the technology failed, not because the missions became too dangerous, because the budget was cut, because the public had lost interest, because the political will that Kennedy had summoned in 1961 had exhausted itself by 1972. The last 3 Apollo missions, 18, 19, and 20, were canceled. The Saturn V rockets built for them were placed in museums where they remain. The rovers that Scott, Young, and Cernan drove are still on the lunar surface. Nobody has gone back to get them. Tracy Cernan's initials are still in the dust of the Taurus-Littrow Valley, exactly as her father traced them. The plaque on Eagle's descent stage, "We came in peace for all mankind," is still there. The footprints around it are still there. The flag that Aldrin planted is still there, though photographs taken by orbiting spacecrafts suggest the Apollo 11 flag was blown over by the exhaust of the ascent engine at departure. The surface of the moon holds everything that was left there, waiting in the silence and the cold and the dark for whoever comes next. After Apollo, there was silence, not the silence of the moon, not that absolute, airless, billion-year quiet. The silence of an organization that had done the most extraordinary thing in human history and was now trying to figure out what to do next. NASA in the early 1970s was an agency with an identity problem. It had been built around a goal: reach the moon before the end of the decade. And it had achieved that goal, and now the goal was gone. The budget that had sustained 400,000 people and 20,000 contractors had been cut repeatedly as the political winds that had made Apollo possible shifted toward other priorities. The Vietnam War, domestic poverty programs, a public that had watched men walk on the moon 6 times and had, somewhere between the 5th and 6th time, begun to change the channel. The engineers who had built Saturn V, the largest, most powerful rocket ever flown, watched their creation retired. The last Saturn V launched Skylab, America's first space station, in May 1973. After that, the rockets sat in museums. What came next was a different vision entirely, not exploration. Routine access, the concept behind the Space Shuttle, was, on paper, elegant. A reusable spacecraft that could launch like a rocket, operate in orbit, and land like an airplane. It would make spaceflight routine, cheap, reliable, frequent, instead of expensive expendable rockets that were discarded after a single use. The shuttle's orbiter would return to Earth, be refurbished, and fly again within weeks. It would carry satellites to orbit and retrieve them for repair. It would serve as a platform for scientific research. It would eventually carry the components of a space station. The economics, as presented to Congress in the early 1970s, were compelling. Each flight would cost approximately $10 million. The shuttle would fly 50 times per year. The cost per kilogram to orbit would drop dramatically. These projections were wrong. Not slightly wrong, catastrophically wrong. The shuttle ultimately cost approximately $1.5 billion per flight. It flew, on average, 4 to 5 times per year rather than 50. The cost per kilogram to orbit was higher, not lower, than the expendable rockets it replaced. But in 1972, when President Nixon approved the program, The projections looked reasonable, and the alternative: no American human spaceflight program at all, was politically unacceptable. Construction began. The Space Shuttle was, by any engineering measure, the most complex flying machine ever built. The orbiter, the winged spacecraft that carried the crew and payload, contained approximately 2.5 million parts. Its main engines, 3 of them mounted at the tail, were the most technically demanding rocket engines ever produced, burning liquid hydrogen and liquid oxygen at temperatures exceeding 300 degrees Celsius while operating at pressures that would destroy any conventional engine within seconds. They were reused across multiple flights, inspected and refurbished between each one in processes that took months. The thermal protection system, the tiles that covered the orbiter's underside and protected it during re-entry, consisted of approximately 24 Naus individual ceramic tiles, each one slightly different in shape and thickness, each one individually fitted to its specific location on the orbiter's surface. They could not touch each other. Direct Contarin's flight, Space Shuttle, Columbia, lifted off from Kennedy Space Center. The crew was 2 people. John Young, who had walked on the moon on Apollo 16, commanded the mission. Robert Crippen, flying in space for the first time, was the pilot. The launch was, by any standard, spectacular. Unlike the Saturn V, which built slowly from the ground, its enormous mass resisting the thrust of its engines, the shuttle accelerated rapidly, its solid rocket boosters producing a combined 25 million newtons of thrust from the moment of ignition. Young and Crippen reached orbit in approximately 8.5 minutes. They spent 2 days in orbit, testing the orbiter's systems, the payload bay doors, the maneuvering thrusters, the flight control surfaces that would be needed for the unpowered glide to landing. On April 14th, Columbia re-entered the atmosphere and glided to a landing at Edwards Air Force Base in California. Young stepped off the orbiter and walked around it, visibly delighted, examining the thermal tiles, the engines, the landing gear. He had flown in space 4 times. He had walked on the moon. He had seen things that very few human beings had seen. He walked around the orbiter like a man looking at something he could not quite believe existed. Over the next 4 years, Columbia flew 4 more test flights and was joined by 3 sister ships, Challenger, Discovery, and Atlantis. The shuttle did things that no spacecraft had done before. In April 1984, astronauts from Challenger captured the malfunctioning Solar Maximum Mission satellite, brought it into the payload bay, repaired it, and released it back into orbit. This had never been done. The idea that a spacecraft could serve as a repair shop for other spacecraft in orbit was new. Demonstrated for the first time on that mission, the Hubble Space Telescope was deployed by Discovery in April 1990, and then, after the mirror flaw was discovered, repaired by Endeavour in December 1993. in a series of spacewalks that required astronauts to work with tools, in pressure suits, on a telescope moving at 28,000 kilometers per hour. The shuttle built the International Space Station piece by piece over more than a decade of assembly flights, carrying modules too large for any other vehicle to lift, positioning them with the robotic arm, connecting them with spacewalking astronauts working in the vacuum outside. It carried 355 people to space over 135 missions. It also killed 14 of them. January 28, 1986. Challenger was scheduled to carry the first teacher to space. Krista McAuliffe, a social studies teacher from Concord, New Hampshire, selected from 11,000 applicants to participate in NASA's Teacher in Space program. Schools across the country had arranged for students to watch the launch live. The temperature at Kennedy Space Center the night before launch had dropped below freezing. Ice had formed on the launch structure. NASA engineers from the company that manufactured the solid rocket boosters, Morton Thiokol, had recommended against launching in cold temperatures. Their concern was the O-rings, rubber seals between the segments of the solid rocket boosters, which became less pliable in cold weather and might fail to seal properly. The recommendation was overruled. Launch proceeded at 11:38 a.m. 73 seconds after launch, a seal in the right solid rocket booster failed. Hot combustion gases burned through. The external fuel tank ruptured. Challenger broke apart. All 7 crew members died. The cause was an O-ring failure in cold weather. Exactly what the engineers had warned about the night before. The investigation that followed, led by the Rogers Commission, found not only the technical cause, but the institutional cause. A culture inside NASA in which launch schedule pressure had caused safety concerns to be minimized, in which engineers who raised concerns were not heard with sufficient seriousness, in which the decision to launch had been made without the people responsible for that decision fully understanding what they were deciding. The shuttle program was grounded for 32 months. 17 years later, on February 1st, 2003, Columbia broke apart during re-entry. During launch 16 days earlier, a piece of insulating foam had broken off the external tank and struck Columbia's left wing, damaging the thermal protection tiles. Engineers who analyzed the strike during the mission raised concern. The concern was assessed and dismissed. The reasoning being that even if damage had occurred, nothing could be done about it in orbit, so knowing about it served no purpose. This reasoning was wrong. Opits existed: a rescue mission, a repair attempt, an extended stay in orbit, while options were explored. None were pursued because the damage had been assessed as non-critical. At 8:59 a.m. Eastern Time on February 1st, 2003, Columbia entered the atmosphere, and hot gases penetrated the damaged wing. The orbiter broke apart over Texas and Louisiana. All 7 crew members died. The investigation found, again, institutional failures. A culture that had normalized risk, that had seen foam strikes on previous missions without catastrophic consequence, and concluded that they were acceptable, that had failed to take seriously the concerns raised by engineers during the mission. Two accidents. Two different technical causes. One underlying cause. The same pressure, the same culture, the same failure to hear the people saying something was wrong. The shuttle flew its final mission in July 2011. Atlantis carried a crew of 4 to the International Space Station, delivered supplies, and returned to Kennedy Space Center on July 21, 2011 at 5:57 a.m. Commander Chris Ferguson shut down Atlantis's engines for the last time. He said, "Mission complete, Houston." After serving the world's best astronauts and the finest flight control team in history, the Space Shuttle has earned its place in history, and we will take a final look at an incredibly brave and resilient ship. Atlantis rolled to a stop. The program was over. The 4 surviving orbiters, Discovery, Atlantis, Endeavour, and the prototype Enterprise, were sent to museums. Discovery went to the Smithsonian National Air and Space Museum in Virginia. Endeavour went to the California Science Center in Los Angeles. Atlantis remained at Kennedy Space Center. The workers, who had maintained and launched the shuttles for 30 years, lost their jobs. The facilities that had supported the program were mothballed or repurposed. For the first time since 1961, the United States had no vehicle capable of carrying humans to space. American astronauts going to the International Space Station would fly on Russian Soyuz capsules, paying approximately $80 million per seat. For the next 9 years, the silence that had followed, Apollo had returned, but this time it would not last as long. Something was being built in a warehouse in California, and the person building it had a different idea about how space travel should work. The International Space Station did not arrive in orbit all at once. It arrived in pieces. The first piece, a Russian-built module called Zarya, which means sunrise in Russian, launched on November 20th, 1998, on a Proton rocket from the Baikonur Cosmodrome in Kazakhstan. It was 6 meters long, weighed approximately 19,000 kilograms, and contained batteries, fuel tanks, and the basic systems needed to keep itself alive in orbit while it waited for the next piece to arrive. It waited 17 days. On December 4th, 1998, the Space Shuttle Endeavour carried the second piece, Unity, an American-built connecting module, to orbit. Astronauts conducted spacewalks to attach Unity to Zarya. The 2 pieces became one. This process, launch a piece, attach it, launch another piece, attach it, continued for 13 years. By the time assembly was declared complete, in 2011, the station had been built from 42 assembly flights, more than 1,000 hours of spacewalks, and the cooperative effort of 15 nations whose governments disagreed about almost everything except this. The first crew arrived on November 2, 2000. American astronaut Bill Shepard and Russian cosmonauts Yuri Gagarin and Sergei Krikalev docked their Soyuz capsule to the station and floated inside. They have never truly left, not those three men specifically. They returned to Earth after 4 months. But someone has been aboard the station every day since November 2nd, 2000. Through political crises between the United States and Russia, through the Columbia disaster, which grounded the shuttle and left the station dependent entirely on Russian Soyuz vehicles for crew transport for 2 years, through a glow of schedules and meetings and deadlines. They have days when the experiments go well, and days when equipment breaks and the repair takes longer than planned. They have good days and frustrating days. They also see 16 sunrises every day, exercise 2 hours daily to prevent muscle and bone loss, in weightlessness, sleep in sleeping bags velcroed to the wall, and watch the earth turn beneath them from windows that look out on a view no previous generation of humans could have imagined. The water they drink was their own urine yesterday, recycled, purified, filtered through systems that produce water cleaner than most municipal supplies on Earth. This is not presented to them as remarkable. It is simply how water works on the station. Nothing about living in space is simple. Everything about it, to the people doing it, eventually becomes routine. Elon Musk founded SpaceX in June 2002. Sun and 2 in a warehouse in El Segundo, California. He was 30 years old. He had sold his share of PayPal to eBay 4 months earlier for approximately $165 million. He had decided to spend a significant portion of it on rockets. His stated reason was straightforward. He believed humanity needed to become a multiplanetary species, that keeping all of human civilization on a single planet was an existential risk, that the long-term survival of the species required establishing a self-sustaining colony on Mars. He had looked for a rocket to buy for this purpose and found that the cheapest available rockets were far too expensive for what he had in mind. He had concluded that the only way to make rockets cheap enough was to build them himself. His aerospace advisors told him this was not a reasonable plan. He hired them anyway and started building. The first 3 Falcon 1 rockets exploded. Not spectacularly, not catastrophically. In the way that rockets explode when something goes wrong in the first minutes of flight, quickly and without drama. The first failed at 33 seconds. The second failed due to a fuel leak. The third failed due to an unexpected interaction between the first and second stage separation. After the third failure, Musk stood in front of his employees and said something that people who were there have repeated many times since. He said, "SpaceX is in this for the long haul, and come hell or high water, we are going to make this work." The fourth Falcon 1 launched on September 28, 2008. It reached orbit. SpaceX was the first privately funded company to develop a liquid-fueled rocket and successfully place it in orbit. What happened next changed the economics of spaceflight permanently. In December 2015, a Falcon 9 rocket launched a payload to orbit and its first stage. The large booster that provides the main thrust for the first few minutes of flight, previously discarded in the ocean after every launch, flew itself back to the launch site and landed vertically on 4 landing legs deployed moments before touchdown. The landing was filmed from multiple angles. The footage, watched by millions of people online, showed a rocket booster descending through the night sky on a column of fire, slowing from supersonic speed to a near hover and settling onto the landing pad with a precision that seemed, to anyone who understood what they were watching, almost impossible. It was not impossible. It was engineering. Years of development, thousands of test flights of increasingly capable prototype vehicles, the gradual solution of problems that had never been solved because nobody had previously tried to solve them. The cost implications were significant. A Falcon 9 first stage cost approximately $30 million to build. If it could be reflown 10 times, the cost per launch dropped by nearly 90% compared to expendable rockets. SpaceX began recovering and reflying boosters as standard practice. By 2024, individual Falcon 9 boosters had been flown more than 20 times. On May 30th, 2020, a SpaceX Crew Dragon capsule carrying astronauts Doug Hurley and Bob Behnken launched from Kennedy Space Center, the same launch pad that had sent Apollo 11 to the moon and docked with the International Space Station. It was the first time American astronauts had launched to space from American soil on an American vehicle since the final shuttle flight in 2011. 9 years of flying seats on Russian Soyuz capsules at $80 million per seat. The Crew Dragon seat cost NASA approximately $55 million. Hurley and Behnken floated into the station and were greeted by the crew already aboard. In mission control at Kennedy Space Center, flight controllers who had worked the final shuttle missions sat at consoles that had been vacant for 9 years. Some of them were crying. The rocket SpaceX is currently developing, Starship, is the largest and most powerful rocket ever built. It stands 121 meters tall. Its 33 first-stage engines produce approximately 74 meganewtons of thrust at liftoff, nearly twice the thrust of the Saturn V. It is designed to be fully reusable. Both the first-stage booster and the upper-stage spacecraft returning to Earth after each flight. Its stated purpose is to carry up to 100 people to Mars on a single flight. Whether this will happen, and when, and what it will mean when it does, are questions that nobody can answer with confidence. But the rocket exists. It has flown. Each test flight has gone further and worked better than the one before. The warehouse in El Segundo, where Musk started building rockets in 2002, is long gone, replaced by facilities in Texas and Florida and California that employ thousands of engineers working on problems that 20 years ago were considered either solved or unsolvable. The economics of spaceflight have changed permanently. The question of who goes to space has changed. The question of why, the purpose, the destination, the long-term vision is being answered differently than it was in 1961 or 1981 or 2002. The answer SpaceX gives is Mars. Look, whether that is the right answer or the complete answer or the only answer worth pursuing, those are questions for the people who will live with the consequences, which is to say, everyone. And so, after all these decades, humanity still looks upward. The rockets are different now. The people are different. The dreams, somehow, are the same. Somewhere tonight, an engineer is designing a spacecraft that has not yet flown. Somewhere, a child is looking up at the moon, wondering what it would feel like to stand there. And somewhere above us, satellites drift silently through the darkness, following paths first imagined by people who dared to believe that the sky was only the beginning. We have traveled farther than our ancestors could ever have imagined. Yet, the universe ahead of us is still unimaginably vast. There are planets waiting to be explored. There are mysteries waiting to be understood. And there are stories that have not yet been written. But those are journeys for another night. For now, let your thoughts become as quiet as the stars above. Let your breathing slow. Let the darkness feel peaceful rather than empty. And as the earth turns gently beneath the endless sky, allow yourself to drift into a deep, restful sleep. Good night.